classmates. My name is Zhou, and I'm come from Nanjing Agricultural University and from National Engineering and Technology Center for Information Agriculture. I'm very happy to have the opportunity to share my works with the researchers. My topic is exploring the application of software robotics in crop contact detection. Before my introduction, I will first introduce my team, NetC, a lovely team. Our team is currently has 13 professors and 4 associate professors. The boss is Professor Cao Weixin, and I'm on the far left side of the photo. Our teams mainly focus on using smart agriculture to realize to ensure food security. As we all know, we have faced many challenges such as rapid growth in population, limited arable land, increasing shortage of water resources, frequent extremely climate events. So ensuring national food security is a major task of each country for now and a long time in the future. My major is robotic engineering, and for the perspective of smart agriculture, creating intelligent monitoring and harvesting equipment can help improve agriculture operations in efficiency. And my previous work focused on developing a crop phenotyping equipment, such as mainly contains 2 parts: multispectral imager and phenotyping robotic. Also, there are many major commercial multi-spectral imager available now, but they have 2 main limitations in the field of agriculture phenotyping monitoring. The first one is high complex optomechanical structure, and the second one is whole real-time image spectral processing. So that which is not conductive to the analysis of crop phenotypic parameters. So my work has I have designed mosaic filters with breakthroughs in snapshot and small FOV imaging technology, and developed an information processing system for online processing of sensor data. Our spectral commercial has our multispectral imager has been equipped on Dajiang drones for phenotyping monitoring. However, also UAVs are unable to meet the demand for close. However, the use are not unable to meet the demand for close-range, high-throughput phenotyping monitoring. So I also developed a universal phenotyping robot for paddy and dry fields. The robot structure is as shown on the left image. It mainly about 5 parts. The first, it has adjustable mobile chassis. It can check with its check with can adjust from 1,000 to 1,400 and to 1,600 millimeters, and it has its motion control unit. It has a motion control unit, and robotic arm is equipped on the robot. The robotic arm can equipped with many sensors such as LiDAR and multispectral imager, and an information processing unit is to realize the parameter calculating, and solar panels and batteries is for the power supply to ensure the robot with a working time for 4 hours. And the second, the right part is the structural composition of the robot. And this is the works of the work operating of the robot video. And we can so it can autopilot and sensor gimbal rotation and can with height adjustment, gimbal elevation, angle adjustment, and data collection process. We have combined our multi-spectral imager with the phenotyping robot and has experiment in Rugao and Jiangsu. The two videos show the phenotyping robot with the multi-spectral imager in the rice production areas and rice breeding areas, with the advantages of adjustable wheelbase and autonomous navigation. We can see the robot can walking easily on the paddy land. So as you can see, my previous work mainly focused on the non-contact sensing, but however, some proper matters must be monitored through close contact method to ensure accuracy, such as SPAD 5002, to use it to evaluate the relative content of chlorophyll in leaves, and PM 200 5000 to evaluate the fluorescence of parameters, especially so variable sensors monitoring the surface temperature and humidity of the blades. Wearable sensors are emerging crop physical parameters monitoring devices, which have received a lot of attention for their non-destructive and good good comparability. Wearable sensors are mainly composed of sensing wires, signal acquisition, and power supply, among which the signal acquisition and power supply, we can say, are bulky and cannot stick on the leaf, so they cannot realize the relap to stick on the leaf. So integrate another method is integrating wearable sensors into biometric robotic arms, allows the integration of power and signal transmission modules onto the robotic arm and achieving a similar wearable contact effect. The rigid robotics represented by 6 degrees of freedom robotic arms have been widely used in industrial products such as on the car and on the plane profession. But the rigid robotic arms are prone to damage crops during contact operations. As we can see, if we use the rigid arm to climbing the apple, the rigid part will damage the apple and also affect the monitoring accuracy and reducing crop yields. So I have designed a soft robotic arm to solve the problem. The robotic arms are made from high flexible silicon, as we can see on the left, and it can generally divided into symmetrical upper and lower parts. The upper part is a cavity that can expand after inflation, and the lower part is a solid structure which is a constant length. So when the upper part is with high pressure, it will expand and to make the overall deformation for the soft arm. And multiple soft robotic arms can working together can achieve flexible clamping for touches, especially for fruits, for eggs, and for other crops. But the traditional soft robotic arm relies on overall bending deformation clamping. So as we can see, for one robotic arm or 3 robotic arm clamping, they are suitable for grabbing for 3-dimensional objects and it was difficult to achieve tight clamping for crop sleeves. So I have designed a new type of robotic arm. The front end of the robotic arm is countable. During the clamping process, it can achieve both flat clamping and curved clamping, and and therefore we can place wearable sensors like this at the front end of the robotic arm to testing the leaves and the fruits. I called the control method is with variable stick control method, and this is the sectional view of the robotic arm. The upper we can divide it into three parts. The upper part, what we call is the deformation part. It mainly include about two cavities. The first cavity is with a long cavity 1 and a short cavity 2, and the immediate part is a solid part which will restrict the deformation, and the lower part which we call is the variable spherical part with a cavity 3 to control the stiffness of the robotic arm. When we use the robotic arm for fruit clamping, the cavity 1 and cavity 2 will with a high pressure, and the cavity 3 will with a low pressure, so that the high pressure on the upper part will cause the overall deformation of the robot. And as the cavity 3 with a lower part, it will with same stiffness with the silicon. So the robot arm will has a high overall bending. And when we use the robotic arm for leaf clamping, the cavity 1, cavity 2, and cavity 3 will also have high pressure. Because the cavity 2 and cavity 3 with the same high pressure, the front end of the soft robotic arm will not deformation, so it can use for the leaf clamping. The soft fingers will bend and deform towards one side when loaded with air pressure, and the bending deformation state of soft fingers at different bending angles can be calculated. By establishing a coordinate system with endpoints O1 and O2 as the origin, the x1 and x1 coordinates of the second joint endpoint O2 and the x2 and the y2 coordinates of the fingertip endpoint over 3 can be calculated from the tips. In order to determine the optical structural parameters, we simulated the robotic arm, and through the simulation, the parameters of the deformation layer, intermediate layer, and the variable stiff layer to achieve the desired deformation effect. As we can see, if the silicon is too thin, it will cause the deformation and distortion, resulting in loss stiffness function. And if the thickness of the silicon is excessive, it will cause the overall bending and loss the stiffness function. So we determine the thickness of the silicon layer to be 2 millimeters through the simulation. And this is the structure of the soft robotic arm. And the left part is the 3 wheels of the robotic arm. And the soft finger stack, the soft reading, and this is the first the soft robotic arm reading diagram, and the soft robotic arm structure diagram and the sketch diagram. As we can see, the upper part is the deformation part, and the and the solid part is the intermediate part and layer, and the lower part is the variable stiffness layer. To prepare for the soft robotic arm, we use the distributed module, a step module method involves the modeling and deformation layer, intermediate layer, and variable stiffness layer of the soft robotic arm separately, and then bonding them together with silicon gel. And we can see for the deformation layer, we first use the 3D printer to making the mold and casting the silicon, to make the deformation layer, and with the similar operations, we can use the 3D printer to print for the intermediate layer mode and the variable stiffness layer mode. And after casting for the deformation layer and the intermediate layer and the variable stiffness layer, we can use the bond, use silicon to bond them with integral casting. And the left shows the control system of the robotic arm. The left shows the protocol of the soft finger drive and its control system. The soft finger angle control is used a PID, which to control the mainly two pressure of the soft finger. As we can see, the deformation part with the cavity 1 and cavity 2, they are with the same pressure, and the cavity 3 with the other pressure. So there are two PID control systems, and this picture shows that diagram of the soft finger bending geometry model. And this is the control software of the soft robotic arm. It was programmed by a PyCharm. It has 5 functions and include set stereo commutation parameters, set the deformation pressure value, set the variable stiffness error pressure value, and display real-time pressure curve and data buffer to save the data. This is the video for the leaf clapping. As we can see, it mainly called 3 steps for the prepare and clap and the raise. The deformation layer with cavities 1 and cavity 2 are inflated with high pressure, while the stiff layer cavity 3 is maintained at high pressure, which is the same with the cavity 2. So it can causing the soft finger to deform and tightly clamp the leaves. Because the cavity 2 and cavity 3 with the same pressure, so it will have a high stiffness and will not deformation too much, and to stay a plane structure for the leaf clapping. And for the fruit clapping, as we can see, we use a robotic robot, a rigid robot, and a soft robotic arm to clap a fruit. We use the YOLO algorithm to find the position of the fruit, and the deformation of the layer. The deformation layer of cavities 1 and cavity 2 are inflated with high pressure, while the stiff layer, cavity 3, maintains low pressure and the same stiffness as the soft finger itself. And because the cavity 3 maintains a low pressure, and it will have the same low stiffness with the soft finger itself, which will cause the soft finger and the soft arm to deform as a whole and achieve the action of clapping the large 3-dimensional objects. My other work is to make the wearable sensors, and the wearable sensors can monitor early stress signals in crops. Composed with the rigid sensors, the soft sensor with the advantages of flexible to adapt to complex shapes, and better environmental adaptability, and low cost for large-scale production, and lightweight and thin. And this picture shows the principle of the crop wearable temperature sensor. As we all know, the mental resistance where has a linear variation with the temperature. So if we got the resistance of the mental, we can also calculate the temperature by the mental resistance. We use the PDMS as the common subject for the flexible sensor, because the PDMS with a good, excellent extensibility and almost not absorbable visible light. To make the wearable temperature sensor, we first made a coating mask. The coating mask is cut and processed by a laser engraving machine, and the mask material is acrylic board. And we use the coating machine to coat the film. Under the vacuum, the boiling point of the metal decreases significantly, and when heated, they become gaseous and condensed on the substrate that is not covered by the mask, forming a cover film, as shown in this picture. When it captures the temperature sensing wires using PI and PDMs, the signal is transmitted through ultrafine wires, and the temperature sensing wires are adhered to the ultrafine wires using conductive silver glue. And we first place the sensor in a constant temperature chamber and observe the exchange in temperature and sensor resistance. As we can see, it can be found that there is a good linear correspondence between the resistance and the temperature. And the temperature wearable sensor is attached to the plant leaves using which using van der Waals forces provided by the PDM substrate, and temperature monitoring is achieved through responsive existence of temperature curve. And I have also made a crop wearable humidity sensor. Its principle is that the laser-induced graphene LRG is mainly based on the photothermal effect and chemical reduction of laser radiation of the surface of plastic substrate. We can use 3 steps to make the wearable sensor. First, the laser-induced substrate PI film for patterning, and then the solution spread on the PI film, and at the last we lay in the patch substrate and adhering place for humidity monitoring. And this picture shows the materials and the machines to make the wearable humidity sensor. And we first choose the flexible subject materials and use the equipment such as laser engraving machine and coating machine and other machine to make the sensor, and then process and use the process technology to prepare for the flexible sensor, and at last we can establish a system integration. Because this is the picture of the humidity sensor. Because this is a new work, so we just tested in the room. The stand direction of the finger spacing and laser induced power, the spacing is 200 micrometers to 500 micrometers, and we use the laser-induced power is 3.5 watt and 5 watt to 5 watt. We test it in the room, in the indoor room, and the humidity is about 20%, and the laser speed is 200 millimeters per second. As the finger spacing increases, its characteristic gradually weakens. Moreover, as the laser-induced power increases, the capacitance characteristics becomes more stable. This is overall of my work, and this is a picture of my students. I now have 25 students with 7 doctorate candidates and 30 master's candidates. I'm very happy to collaborate with more wearable sensor teams, and welcome to Nanjing Agricultural University. This was all my introductions. Thank you.
Yeah, thanks very much for Professor Zhou's excellent lecture. Especially he introduced the work about field robotics for rice breeding and soft robotics for the crop, especially some wearable sensors design and research. That's really excellent. Yeah, maybe I guess some questions well from our audience. If anyone has questions, can unmute yourself and then ask to the Professor Zhou. Yeah, before anyone have questions? Before the audience question, yes, I have a question about the wearable sensors, Professor Zhou. I'm not sure yes how the costs. I mean that when you design and make wearable sensors for the humidity or something, how much it costs? Is the price very high or low?
The cost is it's very cheap, very cheap. You can it's for one sensor. Its cost will not no more than 1 Chinese yuan, and no more than 0.2 US dollars maybe.
Okay.
For one sensor.
Okay. Yeah, so that's the price is reasonable. It can be widely maybe used for the phenotyping information acquisition. Yeah.
I have a small question. I'm Dr. Mustafa from Bangladesh. Can I ask a question?
Yeah, sure. You're welcome.
Yeah.
Okay, my question is that whether this wearable sensor will vary in its structure and composition from crop to crop.
Sorry, can you repeat it again?
Yes, of course, I will repeat it.
Yes, thank you.
My question is whether the structure and the composition of this humidity sensor, as you have shown here, will vary from crop to crop.
Yeah. So I will answer the question for two aspects. The first, if for the real wearable sensor, because its cost is very low and it's very cheap. So for most the wearable sensors, it was will made a lot of wearable sensor to stick on maybe on several leaves to have the average parameters, and for our method, for our soft robotic arm method, we use the YOLO version 7 to collapse the leaves and collect the leaves, and because we have the navigation, we have autonomous navigation method. So I can use the robot with the robot and with the working chases. It can got many leaves and many crops and the parameters. Oh, that's all. Thank you.
Thank you very much.
Thank you.
Any questions from our audience? Just added a comment. Yeah, Professor Zhou. Yes, I just thinking. Yes, if you use this wearable sensors to different crops, how you make sure? Yes, that the measure accuracy, yes, keep stable, because the different crops maybe have a different the features. So you need to change the model or just change the parameters or some other things to make sure the measurement is stable and in a good level.
Oh, okay. Thank you. Thanks for your question. And we are engineering, so we want to use a common method that we can common method is suitable for more crops, but for the real wearable sensors, it will designed for different substrate structure and to stick on different leaves. But for the leaves also will grow and will cause the wearable sensors that cannot use. But for our method, we want to find that we can use the pressure from the finger, from the robotic arm to realize the clapping, and for this method, the structure of the leaf is not the key point that it's not the key point that it's not the key point for prevent the stick on the leaf, because the robotic arm can give the enough pressure. So the first question is the answer for the question is I want to use the robotic arm to give some pressure to realize the stick the stick on the leaf. And the second question is I want to for different crop parameter calculating, and this need large works to acquire many crops and parameters, and to establish a database, and to establish a database that to make a more useful and common and calculating method. And that's my answer. Thank you.
Okay, got it. Thanks so much for your explanation. Yeah.